Okay, cool.
Yeah. Oh, no, in the middle. In the middle.
Oh, do you want just the slides?
Just, yeah, just a slide, probably, yeah.
Okay.
Right, cool. Yeah, I guess I can start. Then, yeah, today, yeah. So first of all, thank you for inviting me to give the talk. And yeah, today we'll talk about quantum simulation for chemistry and first quantization with any basis set. So this talk will be based on this paper and PJ, which was recently published in PJ Quantum Information. And before I start, I just would like to thank my colleagues who work on this project of team, who was a PhD intern at Riverlane and his PhD student at Oxford University, and then my colleagues Marius, Christoph, Bjorn, and Robert, who work with me at Riverlane. All right. Yeah. So this is the structure of my talk. So I will start with the introduction, very basic, just to remind people what is a first-second quantization, because this will be important for the rest of the talk. And then I will show some examples for chemical systems, which we think might be suitable for simulating chemistry in first quantization. And then I will give you a short overview of quantum algorithms for first quantization, because this is not, of course, a new subject. People have been working on this for 3 decades at least. And then I will introduce our main innovation, which we developed in this work. And in the end, I show you quantum resource estimates, basically how many qubits and gates you need in order to simulate some interesting systems on the future for quantum computers. And then I finish with a summary, some outlook on what we work on and yeah, where we think this can move forward. All right, I think also because the talk, as I understand, is 40 minutes or 45-minute seminar. No,
we can carry on.
Yeah. So I think I don't want to talk for 45 minutes. It's quite tiring. If you have questions, I think you can just interrupt me and ask. I think it will be easier than to accumulate questions at the end. So feel free to interrupt. All right. Yeah, so let's start with the introduction, basically. What is first and second quantization? So we consider this generic Hamiltonian, and this is expressed in the first quantization. So you have a one-body term, which acts on one particle at a time. It can be electron. Then you have two-body term, which describes interaction between two particles, right? So it acts on two particles at a time. And here we just wrote this in a real space representation. So in quantum chemistry, this will be conventional Coulomb interaction between electrons. Then you have a kinetic energy operator, and then interaction of electrons within nuclei. So this is and what you can see, there is explicit dependence on the number of electrons. So operators act on a specific electron. Right, so then the goal of quantum chemistry, one of the goals is to try to solve the Schrödinger equation, which is very hard. And then when you solve the Schrödinger equation, Hamiltonian doesn't care about if you consider fermions or bosons. It's your constraint, it's a Pauli principle, so that which you impose on the solution, saying that when I exchange two particles, the wave function should change sign if it's fermions and should be a plus sign if it's bosons, right? And so typically when in textbooks, all equations are introduced usually in this real space representation, but you can change your basis set. You can expand your wave function into some orbital with just a single orbital basis set. P here indicates some quantum numbers. And then you can express these equations in a matrix form when you discretize your space, basically. And this is the same equations, but just in a different basis set. So again, you have sum of electrons, and then here it's not an operator, this is just a matrix. So you calculate these coefficients using some quantum chemistry software. And then here it's a four-dimensional tensor. Basically, the two-body term becomes four-dimensional tensor. And then this PQ is, you can think about it as a matrices of the dimension d by d, where d is the number of basis functions. And there's zero everywhere apart from PQ position where it's equals 1. So this is just expansion into some matrix basis set. And then again, you need to impose these constraints, right? The wave function should change sign. And you can notice that the Hilbert space has dimensionality d to the power of n, where d is the number of orbitals and n is the number of electrons. So the Hilbert space grows exponentially in the number of electrons. but polynomially in the number of basis functions. And then there is another formalism called second quantization. So the reason people introduce this is because working with these objects where you need to asymmetrically wave function is quite awkward, can be quite tedious work. So what you do, you move these anti-symmetry constraints into your operators. This is why it's called second quantization. And then you forget about this anti-symmetry in your wave function. You just expand it into so-called equation number states, where each number here, n1 up to nd, belongs either 0 or 1. And then your anti-symmetry constraints are encoded in this anti-commutation relationship. But Hilbert space here is quite different. Now your Hamiltonian X from a Hilbert space of dimensionality 2 to the power p, where d is a number of base function. And you can notice that this Hamiltonian doesn't care about number of electrons. It doesn't matter how many electrons are in your system. So it's better to use this Hamiltonian if you have non-conserving number of electrons in your system. But in chemistry, usually we consider molecules with a fixed number of electrons, so maybe this approach is not so bad. Okay, and so this is basically different between first and second quantization. And then it was quite early realized, you can ask, okay, how can I describe a wave function in these different Hilbert spaces if you have qubits? So in the second quantization, as I said, you have a state, and you just specify which orbital is occupied and which is off by 0 or 1. So you have a d basis functions, and because there is a for each basis function you have one qubit, you need d qubits, and then you can create any linear superposition from this Hilbert space. So you just the number of qubit scales linear with the number of basis functions, and then in first quantization you have explicit dependence on the number of electrons n, and for each electron now you specify what orbital this electron occupies, and because there is d orbitals, you just need to enumerate them. You only need log d qubits to specify, to have a binary representation of this orbital. So in total, you will need n log d qubits, and it was quite early noticed that you can get exponential separation when you fix the number of electrons and you try to increase your size of your basis set so as to calculate energy more accurately. You can see that at some point there is exponential separation between the number of qubits, and first quantization clearly becomes more favorable than second quantization. What is not trivial is to understand how circuit depth, for example, changes if you modify just a framework from second quantization to first quantization. Even if you use the same quantum algorithm, for example, factorization, or you try to estimate energy with quantum phase estimation, how this framework will change your circuit depth and T count and so on. All right, and this is what we wanted to investigate. But I think the question one can ask, are there reasonable number of electrons and size of the basis set by first quantization actually important? And I would give the comment that maybe it's not, because, for example, people say Gaussians is a compact basis set, so you may not never be in this regime. But I think it's not quite true. So basically, you can look at different basis sets. Let's say we start with a plane base or real space grid representation. This is just the numbers you can pull from some DFT software. For example, you can calculate how many electrons per volume you have in nickel oxide, so around 1.3 angstrom to the power minus 3. And then how many plane waves you need in order to converge calculation for SG15 to the potentials. And you can see that the number of plane waves is significantly larger than the number of electrons. And similar estimates you can get for real space grid. But also if you consider molecular orbitals, for example, quantum Gaussian orbitals. And just for carbon, you have 6 electrons. And if you take a large body set, augmented correlation consistent triples at the basis set, then you have 46 contracted Gaussians. And there is a regime in chemistry when we would like to do calculation with such a basis set. And sometimes even people make uncontracted Gaussians, which increase even size of your basis sets further. So it seems there is a room for first quantization when we want to target high precision calculations. All right, and let me just show you some examples of chemical systems where you may want to use first quantization. So one reason when people say, oh, yeah, the number of orbitals is usually the same as the number of electrons, You hear this sometimes from people in quantum computing, but the reason they say it is because they benchmark the quantum algorithm against so-called active space problem. So when we try to simulate chemistry, and if the system is strongly correlated, usually we separate the problem into two steps. In the first step, you try to choose a small subspace in your Hilbert space. It's called active space. To account for so-called strong correlations, static correlations. So to account for multi-determinantal nature of your wave function. And indeed, in this case, the number of electrons can be even smaller than the number of orbitals. But if you interested in total energy, you still need to do the second step and to calculate so-called dynamical correlation. And usually this is done with some perturbation theory. And the number of orbitals there is actually much larger than the number of electrons because you need to go in the full space. And then in material simulations, we actually really separate problem in the active and active space and the dynamical correlations. So we're always interested in total energy calculations. Right, and let me just show you a few examples to show that this dynamical correlation, they're actually not small. If you're interested in predicting properties of materials or molecules, you need to get the total energy. So this is one example. So yeah, if you consider iron porphyrin and would like to calculate the spin gap just between triplet and quintet state, so you can choose some active space where you have the number of orbitals is around the same as the number of electrons, and the spin gap is around 30 millihartz. And then you can apply, you can calculate dynamical correlations on top of that, and you can see that it's around 20 millihartz. And then the total gap is reduced more than by a factor of 2. So when we speak about dynamical correlations, so they are quite important if you would like just to predict the spin gap properties. Similarly, if you are interested just in potential energy surface, and this is another molecule, copper oxide, and you just start stretching it so as a radiation coordinate. And you choose some active space and do, for example, CAS calculations or DMRG. You can see that in the active space calculation, you can produce wrong local minima, which should not exist. Then you can do some additional calculation, for example, optimize the orbitals. But the point here is that you still need to account for the dynamical calculation, which accounts for 10 millihartz. So it's not just sub-millihartz problem. And the hard bit is that there are many algorithms how you can account for this.
What's the cost of the scaling of that perturbative calculation of the
Yeah, so basically it scales polynomially in a number of basis functions. I can't remember, it depends on the algorithm what the prefactor and the not prefactor.
So it's a small portion of the full cost in the very end.
Yeah, so I think, and this is what people try to argue when they consider quantum algorithms. They say, okay, the hard problem is to account for static correlations and then dynamical correlations. In complexity terms, it's simple because it scales polynomially with the system size. But there are many algorithms to do this, and the hard bit is to make them all agree within 1 millihartz for not just for one geometry, but when you try to stretch a molecule to make different algorithms agree within 1 millihartz, for example. So, and it's just to emphasize, even though perturbation theory scales polynomial in the system size, it doesn't mean that it's easy. And just to show you, I'm not stating that this system is, for example of a quantum advantage type of system. Probably with modern HPC, with GPUs, with modern software codes, you can solve this problem. But it's just to illustrate it's really hard. Quantum chemistry is really hard. All right, and then the next problem is more from periodic calculations. So there is a system model called uniform electron gas. It's basically electron moving in a field of in a uniform positive background. And what you can do, you can then change the volume of this or density of uniform electron gas, and there is this point similar to when you stretch H2, Cauchy-Fisher point, where unrestricted solution becomes lower in energy. You have spin symmetry breaking. And so the unrestricted Hartree-Fock solution becomes lower in energy. And usually this is the first indication that you have some static correlation, static correlations means you have some degeneracies and so on. And there are several benchmarks published in these papers where you can, for example, compare what is correlation energy of different classical algorithms with respect to these accurate results, SCI, QMC, and you can see that the deviation is more than 1 millihartz basic per electron. So it just indicates this is hard calculations, and this is just a small system with 14 electrons and 173 orbitals. But then we need to scale this. We want to calculate larger systems for 54 electrons. And then it was shown in this paper that to converge calculation with 1 millihartz just per electron, you need more than 2,000 plane waves. So the number of orbitals is again much larger than the number of electrons.
That's quite a high energy, high error potentially, because that's 54 millihartz.
Yeah.
For the system. Yeah.
Exactly. Yeah. So yeah, definitely. Yeah. It's a large error. And again, this is a result from 2019. I guess today you can improve this and make a better agreement.
I'm just curious.
Yeah, I think this algorithm, they all technically scale polynomially because they have some approximations in so for example, here you can add more letters like Q, for example. And with FQMC, I think it all depends on your trial wave function. And then if you improve your trial function. And here, I think the authors already use some non-orthogonal rate determinants. Yeah, I'm not familiar very much with FQMC, but Alex probably can comment.
Yeah, that will scale exponentially, but you can get with quite a low prefactor.
Yeah. Right. And again, I don't want to claim that this is a quantum advantage type of system. So maybe we can, if we just push classical software and giving that we have access to modern GPUs, which maybe, yeah, it's a solvable problem. But it's just to illustrate that there are hard problems of chemistry where you need to perform large scale calculations to get decent results. All right. And now, right, I think this is what I basically was saying. That majority of quantum algorithms that we develop, they benchmark against this first problem, static correlation problem. But the problem is that if you do this step, then we don't know how to access dynamical correlations actually on a quantum computer. We know how to do this in a classical, but we don't know how to do this on quantum. And one way to solve this problem is, of course, let's just scale our algorithms, like increase the size of your active space, include more and more orbitals, and then just reach the conversion limit. And in this case, it's not clear obvious that the first or second quantization will be the most appropriate way to deal with this problem. Yes. On the quantum, so I will come to this later. So we use quantum phase estimation with a so-called qubitized quantum walk operator. So it's not very short. All right. Let's move now to a quick short overview what people did in the first quantization, because as I said, it's like, yeah, people have been working on this for 30 years. It's not new. And then I separated it into three columns. Basically, yeah, the first column is time evolution with real space and plane waves. Then there is time evolution with molecular orbitals. And then there are works on resource estimates just for ground state energy estimation, where people actually try to count how many gates qubits you need in order to do ground state energy estimation. And this is not a comprehensive list. There are many other nice works, which I didn't include here, and I apologize for this. But I think this is just a representative basis, which shows how the field develops. So actually, the first quantum algorithms, they were developed for real space, and in some sense also for plane waves. The very first quantum algorithms, and they discuss how to do, for example, how to implement kinetic energy using quantum Fourier transform. The kinetic energy becomes diagonal on the reciprocal space, and then we do it back. So, and then there were works by Adams and Lloyd, where they actually propose quantum algorithm which works with any basis set, and in fact they even discuss how to carry out calculations for Hubbard model in first quantization, right? So, and they give some asymptotic analysis of the algorithms. And then there was work by Casale and co-workers, where they considered field space representation, and they considered both electron and nuclei together. So you do time evolution of the whole system. And then there was an algorithm which works in the plane waves. And in all these papers, they provide asymptotic scalings, how my algorithm will behave if I pull all my parameters to infinity, basically. And then on molecular orbitals, actually, there is not much work was done. So as I said, there was this work by Abrams and Lloyd, which in principle worked with any value set. And then there were a couple of works where people presented algorithms for so-called CI matrix. So as I showed before, I said you can decompose your Hamiltonian or wave function into some basis set, right? And this is just for single orbital. You can construct a single selected determinants and calculate matrix elements of your Hamiltonian in this basis set. And this is called CI matrix, configuration interaction matrix. And the good thing about it is that it acts non-trivially on a fermionic space only, but it kills all the, for example, symmetric contributions in your wave function. And yeah, they provided some asymptotic scalings of the quantum algorithm, but no detailed resource estimates were done. And again, as I said, it works in a specific state determinant basis set. And then I'm not aware of any other works in the molecular orbitals in the first quantization. And then, yeah, there was some works for detailed resource estimates, again, in plane wave for real space. And then there was generalization of this on this GTH to the potentials. And basically, when we were looking into this, we realized, okay, there is a room for research, for doing some investigation. Let's now push first quantization with a orbital basis set, molecular orbital basis set, and see how this quantum algorithm behaves. Right. So this was the goal of the project, really. Right. And let's move on to our results. Now I will discuss our paper. So this is the Hamiltonian, which I already presented to you. And what is the starting point in a quantum algorithms? So quite often you want to come up with some, it's called linear combination of unitary decomposition. It means that matrix is given as a sum of unitary matrices with some coefficients. And this is a good starting point for many quantum algorithms. And we know how to do it in a second quantization. For example, you have annihilation creation operators. You use Jordan-Wigner map to map this Hamiltonian onto qubits, and you got your Pauli LCU. So when we were looking in the literature, we realized that actually in the first quantization, we didn't have such a mapping. And so the first step was, okay, let's just try to come up with this Pauli LCU decomposition in the first quantization. And how you do this is quite simple. You look at this matrix. As I said, they form a basis in a space of matrices, but Pauli matrices also form a basis in a space of matrices. So the question is, if I change my basis set, how this coefficient will change, right? It's not like a mapping in a Jordan-Wigner or Brahe-Ptaev, right? It's actually exact transformation. It's the same matrix. It's the same Hamiltonian. It's not a map. And what we did, we basically derived Hamiltonian in this Pauli LCU, and all coefficients are given analytically. So explicit expression for all coefficients are given.
That's just order into the fifth transform or something, maybe into that. Yeah.
Yeah. So this is d to the it will scale as d to the power 4 on top. And yes, d to the power 4 log d. I will show it. Yeah. So. And just to simplify these equations a bit, because there's some thought transform and maybe it's hard to analyze. So let's consider now, let's go back to this real space representation, and I just discretize my real space. And this is a matrix now, and RP, RQ are just defined in real space. So this is just a 2x2 matrix. And then if you simplify those equations which I show, you can see that to get coefficients in this Pauli LCU basis, all you need to do, you conjugate original V by Hadamard, generalized Hadamard matrix, and then divide by a factor 1 over D. And this is already showed you that where this improvement can come from if you use this Pauli LCU. So when you consider second quantization and do Jordan-Wigner mapping, LCU coefficients will be proportional to this V. But here you can see they are transformed. And if V, for example, has a norm which scales quadratic with the system size, you just apply unitary transformation, meaning that this matrix also have a norm which scales quadratic with the system size, but then you divide by 1 over d. So what you can expect is that the norm of this matrix scales not as fast as in a second quantization or as in a original Hamiltonian. And we do see this. For example, if you just generate real Hamiltonian, dense real Hamiltonian, and this is this is for two-body term where it's four-dimensional index. You can see that first quantization here scales as d to the power 3, and second quantization scales as d to the power 4. So you already can have some, you can see where the speedups might come from. And then this is to answer Alex's question. So basically, yeah, you need to calculate this matrix element, and the question is, okay, is it efficient even to do this? And the answer is yes, because so if you look at the structure of this matrix, what you need to do first, you take your original matrix and then you perform this sort transformation. And this sort transformation between indexes, it can be done in place, and it's a very efficient operation. And here I just demonstrated how it works. You basically take each column and then you can permute each column independently. And then what you need to do, you multiply by Hadamard matrix, generalized Hadamard matrix. And luckily for us, this is a well-known transformation. It's called fast Walsh-Hadamard transform, described in the textbooks. So the multiplication by Hadamard matrix can be done in d squared log d instead of conventional matrix multiplication, which is d cubed. Right. So and again, this Hadamard transform applied row by row. And then in the end, we need to add some prefactors. But this algorithm can be performed. Sorry, this shouldn't be n, this should be d. But yeah, in d log d time, and it uses only constant amount of memory. And then here are some examples. For example, if you consider a real space representation with 32,000 basis functions, all these coefficients can be calculated in 17 seconds. So it's quite fast. And then we have an open source package which you can try and easy install. So this is really available. And just to mention, you can use it not just for chemical Hamiltonians. If you just have a matrix and need LCU decomposition of that, you can use this equation. All right, just to summarize. So yeah, first second quantization. The second quantization you uses a qubit mapping, which must satisfy anti-commutation relationship. So you use Jordan-Wigner. Here you change the basis from matrix units to Pauli strings using this XOR and the Walsh-Hadamard transform. And then Pauli strings in the second quantization acts non-trivially on d qubits, factor loop because of spin. And in first quantization, each Pauli matrix acts on a logarithmic size in the number of qubits, right? And then, as I said, you can expect the norm will scale n squared d cube, where n is the number of electrons, d is the number of orbitals. And in the second quantization, it's d force, but you can expect 1 over d improvement for dense Hamiltonians. But generally, real Hamiltonians are actually quite sparse. So we put here a sparsity of the matrix. And generically, it's not clear how what speed up you can get. So you need to do some numerics, basically, and I will show you some numerics about this.
Aleksei, can I ask about your, so the basis is now effectively, which basis function is each electron?
Yes.
Is that the overlap matrix in that basis is no longer the identity matrix because there are multiple copies of the same thing which are related by permutations of the tree. Is that right? So if I swapped electrons 1 and 2 around, then I should get a -1 in the overlap matrix. Does that cause problems somewhere?
I don't. No, I don't think so. I think you can. I think you can. Just normalize your initial state. Yeah, I don't. So okay, maybe the comment that we use orthonormal basis set.
Oh, but even if it was orthonormal, so the difference between phi1, phi2, phi3, and phi2, phi1, phi3 as my choice.
Yeah.
Those are assuming they're okay. Maybe they're okay. So they're not anti-symmetrized.
In the beginning.
In the beginning. Okay. So it's okay. So So you have the overlap matrix is diagonal, but an anti-symmetric thing would be a big combination of all of those. Mm-hmm. Okay.
Yeah. I think the wave function should be normalized. at least, right?
Yeah.
So
I was just
then-
worried about the off diagonals.
Yeah.
That might,
yeah, but I think because it's just a change of the basis, so you still try to diagonalize with matrix. Yeah, because orbitals are so normal, it will not lead to generalized eigenvalue problem. This is the
okay, yeah, yeah.
I think the first step in all of these first quantization algorithms is to apply an anti-symmetrizer to the
Yeah.
thing. I don't know if it's the case in yours.
yeah. So in this work we actually didn't address the problem of initial separation. There are works which investigate this, and this is not a very trivial task, of course. Yeah, how to do this synchronization efficiently. Right. So now let's go to this quantum algorithms. So basically, as I said, this Pauli, so this LCU decomposition is a starting point for many quantum algorithms. So you can use it with a quantum algorithm of your choice. What we consider this quantum phase estimation algorithm. This is just a textbook QPE. And where you apply this controlled unitary operations and implement this controlled unitary operations, or just even unitary, what you do, you need to construct so-called block encoding. So you start with your LCU decomposition, where these W's are unitary matrices, and then you need to construct this block encoding, where you have subnormalization factor, which which makes sure that your M is a unitary matrix. And the subnormalization factor is basically proportional to this one norm of this Hamiltonian entry-wise norm of this of this vector W. And then what is shown in all of these papers is basically the cost of this algorithm will be proportional to square root of gamma, where gamma is the amount of information you need to specify this Hamiltonian. Basically, how many bits you need to specify all omegas, and the number of qubits will be proportional to square root of gamma. And then you need to get the Toffoli count, you also need to multiply by this lambda, which basically dictates how many controlled unitary operations you need to apply to measure the energy with accuracy epsilon. So this lambda is very important in this type of algorithms. And what you can immediately see is that the properties of this LCU decomposition determine the efficiency of the quantum algorithm. So next I will show you how this lambda scales for different systems. And just to say, in order to implement this block encoding, you need to come up with some quantum gadgets that they call select and prepare. And they are well studied in the literature. Prepare almost the same. The prepare operator which we use is almost the same as in the previous works, with a small modification, and it's easy to come up with select operator for LCU decomposition, which I showed you. So I will not show the technical details. You can find this in the paper.
Can I ask a silly question? How does this compare to using the time evolution operator of the Hamiltonian instead of?
Yes. So you can use time evolution operator e to the power IHT, and what you will measure, you measure directly the energy. Directly the energy. Now, if you implement this block encoding and combine it with a so-called reflection operator, so what you will see is that the eigenvalues, eigenfaces of this unitary operator relates to the energies through R cosine. So what you measure R cosine of energy. And so you will need to do some classical post-processing to get the energy, to invert R cosine, but you can do this. And if you carry out this time evolution with the e to the power of IHT, then you need to perform, for example, tritorization. Right? So it's another one way of implementing this. Here, you don't do any tritorization. It's about how to come up with a block encoding and then perform reflection. And in the literature, it was shown that at least for generic quantum chemistry problems, these algorithms show better performance than tritorization-based algorithms.
But then we do have a success probability for the block encoding at each step.
So you do, but you don't need to measure. You don't need to to perform the measurement and then like Newtonian. You just block encode this. Yes.
I have a question about the one norms. So I understand the one norm for the second quantized situation, but is there a simple way of explaining where it comes?
Yeah. Yes. Oh, sorry. Not the right way. Yeah. So this is the LC. So this is LCU. This is a unitary matrix. This is a unitary matrix. All what you do now, you take absolute values of this coefficient and sum them up.
Yeah, but the scaling was something like d to the 4 in second quantized and d cubed n
Yes.
squared or something.
Yeah. So if it was example for when this is dense, I mean this dense tensor. So because it's four-dimensional tensor, and each element is a constant. It's a constant. It doesn't depend on the system size. Then if you just sum up absolute value of these elements, it will scale as d to the power 4 in the second quantization. But here, because of this 1 over d factor, you can see it here. So you can think about this transformation when you apply. So this is permutation, doesn't change the norm. Then you apply Hadamard, but this is just a unitary transformation. So if you're, yeah, the norm will after this unitary transformation, the norm will have the same scale. And then you have additional factor 1 over d, which reduces the scaling from d to the power 4 to d to the power 3.
Why does it reduce it by that to d? Oh, because that
just
actually
because
is
of
d.
division.
Okay.
So
Sorry.
yeah, if you
I
sum
didn't
them
realize it
all
was the
up,
same d.
yeah, this will be d to the power 4, but because you divide it by 1 over 2.
And there was also an n squared.
Yeah, there is additional factor squared in front. So this is
from summation over the pairs of electrons, right?
sorry.
That's just from the summation of the all
Yes,
these electrons.
yes. This is just from this summation. So you do have this d to the power of n squared d cube d4 in a second, and then you can think, okay, when this is bigger than this, when n is square root of d, right? But actually, what we see, yeah, this is analyzing the worst case scenario when your Hamiltonian is dense. But in practice, this can happen later, or actually can happen even earlier. So it can be just a constant factor, or logarithmic factor.
And you say the sparse and dense in terms of the coefficients numbers.
Yeah, how many
Basic.
non-zero coefficients?
Yeah.
Or this.
If you change to another base, that is, you can say this is dense or like a sparse.
Yeah, so the question is how many non-zero coefficients in your original H?
Like this is in terms of like this is Hardeman and that is Pauli's, right? Which you mean like for the second combination is Pauli's.
Say again, sorry?
I mean, this
Yeah.
is the first combination, so I guess you mean the coefficients for the Hardeman gates, and in terms of the second combination, you use Pauli's, so that's the coefficients for the Pauli strings.
Yeah.
I do mean I just want to check it.
Yeah, so in a second quantization, you will have exactly the same coefficients as it here in the starting point. So all
So it's
eigenvalues
like-
of this
so-
Hamiltonian, fermionic eigenvalues, will be also eigenvalues in your second quantized Hamiltonian. So
I think the question might be, if HPQRS is sparse, does that guarantee that
beta
BPQRS?
is yeah, actually not. It's a good question. Not necessarily. Yeah, I think it doesn't guarantee. But what we can see, for example, if you have a symmetric, let's say H is symmetric, then symmetric. You can ask how symmetries in your original H corresponds to symmetries of alpha. Is it still symmetric matrix? And the answer is no, but it will be sparse. The symmetry of your original Hamiltonian will correspond to the sparsity in a Pauli basis. And we showed it actually in this in this first paper, but we didn't study more generic symmetries. And I come to this later.
I'm very interested in how
Yeah.
much the gaps between and to the spots, how much the gaps introduce or like you will introduce more. That's what make the problem become harder.
Yeah, so for some problems, these matrices can be very sparse. So for example, okay, if it's not generic quantum chemistry problem, but just Hubbard model, then it just will be 3 diagonal matrix, right? So it's very sparse. So you can, I don't know, I hope it answers the question. Oh,
Yeah, I'm just interested.
Yeah.
In much difference.
yes. All right, let's see. Yeah, where were we? Right, so let's now calculate this one norm. And this is for some realistic quantum chemistry tournaments, basically. So this is example just H4, located on a square, corners of the square. And yeah, this is the blue lines are calculations based on second quantization, and red is based on first quantization. And this is just changing the formalism. Everything else is the same. All matrix elements, geometries, everything the same. Basis is the same. Just change your formalism. And you can see that for H4, the norm is smaller even for number of orbitals. It's not even in an asymptotic regime. And we can see some speed up, but it's less than 1 over d. Then we can see that another system, for example, iron sulfur cluster. And yeah, again, we see the asymptotic speed up, but it's unfortunately not 1 over d. And you need quite large body set. You need around 500 orbitals. But I must say that actually here, the reason we don't see larger speed up is because for this system, we use 14 electrons, and the dominant contribution in the norm was just from one body. And but in 2 body, we do get a larger speed up. And then we also considered, okay, because the formalism is general, we can also look at real state grid, such as, for example, Joule plane waves. And then let's see how it performs for uniform electron gas, for example. And the norm scales, sublinear with a number of grid points, but in second quantization, it will be quadratic. And you can see here we got more than 1 over d improvement. And the reason is, we think, is because uniform electron gas also has translational symmetries. And it seems like these symmetries, when you convert this matrix into Pauli basis, correspond to sparsity of your Hamiltonian. So there is significant improvement in the norm. And then, of course, as I said, we're not the first who work on the first quantization, especially in the grid-based approaches. And so there is another work which was published in 2021, where they perform detailed costings of the algorithms, and they work with a specific plane wave base functions. And the good thing about plane wave is that all matrix elements are given analytically. It's a simple equation. You can approximate it on a quantum computer. You can come up with quantum circuit which will calculate these elements. And what we see is that their norm is actually a better asymptotic scaling, but for reasonable number of basis functions in the asymptotic regime, the norm from real space representation, the first quantization, is actually lower. So even though you don't do well asymptotically, there is some regime where you can still get some advantage for previous algorithm. I guess the point of this is just, it's not only asymptotics which are important, but the question is how it behaves in the classical. And then we carry out some resource estimates. Basically, we took these algorithms and let's just calculate how many gates you need, how many qubits you need. And this is just this system, uniform electron gas with 14 electrons and 500 orbitals. And to perform this algorithm, so you can see, depends what you minimize. So you can minimize, for example, the number of qubits you need. So you need around 256 logical qubit and around 10 to the power 7 Toffoli gates. And it is improvement as compared to previous work, for example, and it's significant improvement as compared to second quantization. And again, so here, when we compare the second quantization, it's literally just change of the formalism. The many algorithmic primitives are very similar. And then for larger system, we can see that the number of logical qubits is lower than before, and as compared to second quantization, it's order of magnitude. But the number of Toffoli gates will be lower in this previous algorithm. And then we also considered a bit more realistic system, nickel oxide, with a larger basis sets, for example, and more electrons. And we also can see that in terms of number of logical qubits, it's slightly lower than previous algorithms. And then in terms of software gates, is again only for a small system with 8 atoms, it's less than factor of 2. But for larger system, in terms of software gates, we get similar. All right, I think this is all what I wanted to tell you. Now I try to summarize and say a few things, what we are doing now. So yeah, basically what we did in this work, we developed a new Pauli LCD composition inverse quantization, which works with any base set. So what you can see is that if you use, for example, a real space grid, you get significant speedups if you just switch from second quantization to first quantization. And the nice thing about this approach is that we didn't take into account the structure of your Hamiltonian. So now you can imagine if your matrix elements don't have a simple analytical representation, for example, pseudo-potential, which are crucial to make this algorithm practical, you can easily implement them. It's literally just calculating these matrix elements on a classical computer. Don't need to modify your algorithm, just load them and see how it performs. And I must say, so yeah, kind of the next step we would like to do is to incorporate this pseudo-potentials or even project augmented wave method, which is state of the art in classical computation, together with ultrasoft pseudo-potentials. So, and what we did as the first step in this paper is basically to make we made this method unitary. So because project augmented wave methods, the same as ultrasoft pseudo-potentials, they don't keep your orbitals orthonormal. This is the problem which we briefly discussed. That you need to solve the generalized eigenvalue problem. But if you make your project augmented wave method unitary, then you go back to your regular eigenvalue problem. And yes, so we achieved asymptotic Toffoli gate speedup of a second quantization of molecular orbitals, but it was a bit unfortunate that for interesting systems, the crossover was too far, right? So, but I must say this is not state-of-the-art algorithm. What we did, we just did sparse, so-called sparse quantization. What people do, they apply some factorization method to do body term, for example, using resolution of identity, Cholesky decomposition, then the hypercontraction. So we start doing this work. And basically, we can see that the crossover now happens at a reasonable number of orbitals. So in the previous example, the crossover between this is second quantization, this is first quantization, was around 500 orbitals, but now it's around only 32 orbitals. So, which is quite optimistic. And the scaling of lambda, for some system, we see it's either linear or sublinear, actually. And then for one of the systems I talked about today, for this copper oxide, we again see that the number of orbitals is only a factor of 3 larger than the number of electrons, and you get this crossover when first computation becomes better. So I think hopefully we'll finish this manuscript here, and yeah, hopefully we'll finish doing this detailed resource estimates, and we will see that the crossover happens in an interesting regime, in the practical regime when the basis set is quite realistic. Sorry, no. Oh, what happened? Okay. Okay. Yeah. So then, as I said, method can be used with any Hamiltonian. Doesn't have to be actually quantum chemistry. It can be some other Hamiltonian, and even if a matrix element don't have a simple representation, you can use it. And also, I think we can investigate it now further and go beyond quantum phase estimation and see maybe this formalism will improve some other quantum algorithms. And this is one of the possible research directions, basically. All right, and then just before I finish, I think it's very good audience for this slide. Probably the best audience. So yeah, we are hiring in different streams, engineering, quantum science and internship, and then so we have PhD internships, which we now open for applications, both in UK and US, and then we have also summer internships, which also if you're not doing your PhD, you can apply for some internship. Yeah, come work with us, and just to show that this project actually started with as one of the one PhD intern joined our company, we decided this was one of his tasks to work on this first quantization algorithm. All right, I think I'll finish on this, and then yeah, if you have questions, yeah, let's have a chat. Yes, thank you. Yes.
Yeah. So why can't I do this? The one over D comes from doing the Hadamard.
Not only. So there is
Where did that one over D come from?
yeah, but so I think it comes from the fact I'm not quite certain actually where it comes from. Oops. But the way I don't know why it's exactly 1 over D, but you can maybe rationalize why there is a lower, why you can expect some speed up, asymptotic scaling speed up. It's because this Hamiltonian is decomposed into matrices which are zero everywhere apart from one element, right? And now you decompose into Pauli matrices which are unitary, but they're much more dense, right? So I would think that the weight of these coefficients might be lower the more dense your LCD, your unitary matrices. This is just one intuition, but it might be not quite correct. This is, but how exactly this 1 over D comes from, I can't remember. 1 over D comes from the fact that you have two bodies. So actually in the one body is just one square root of D.
So is your matrix, I think I was misunderstood at the beginning. So the matrix decomposition for the first quantization is the matrices only have ones at indices P and Q? Okay. And that's a full D by D matrix.
Yes, yes. So this is D by D, and index I indicates that this matrix in a tensor product with identity matrices.
Right, so it would be identity, 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 this matrix at position I.
Exactly.
Yeah. Okay.
So the full matrix is still in dimension D to the power of n.
Yeah.
But because, and actually this is why quantum chemistry is good, because Hamiltonian is not just on the matrix, it has a lot of structure. It's made of small tensor products.
And your Pauli matrices in the Pauli decomposition are also D by D. Oh no, they're
yeah, they're D by D.
okay.
They're D by D.
So I guess this is a more fault tolerant setting, but if you're doing something more near term, like you're just driving time simulation, people typically don't put things in a Pauli basis. They would do some 6 circuits. Why could you do this instead? Is there like an obvious reason why this?
So with quantum arithmetic circuits, it's actually I think they're even more fault tolerant than this Pauli LCU, I would think. So yeah, for example, in this paper, we use quantum arithmetic circuits in order to approximate Hamiltonian coefficients on a quantum computer. But they might have larger prefactor. So in a near-term regime, actually this might be more efficient.
Yeah, and then if you do like a split operator approach.
Oh, for example, yeah, if you do, so this is another actually thing which we're currently working on, trying to, as I said, we use QP with qubitized walk operator, but what if you just do tractorization time evolution? What is the cost of the algorithm? Do you get any advantage compared to second population or things like that?
Or even if you just do trotterize split operator, so you're aiming for something more near term. I don't think I've seen anyone do that in a Pauli basis.
No,
in first quantize, because then you could just do Pauli gadgets.
Exactly.
It would be really simple, and you wouldn't have all these like, I don't know. You mentioned pseudo potentials, and the thought of doing that with quantum arithmetic, for instance, is not.
Yes. I think you're right. Yeah, I also didn't see. This is why we basically came up with this Pauli LCU, because when we looked at the literature, there was no simple decomposition. Asymptotically, those algorithms, I think, now I know algorithm you described, where you indeed can do quantum mathematics in a real space to do this visualization. But I forgot what I wanted to say. It was a too long a flow. Yeah, but basically, we didn't see. They asymptotically they will be better because of quantum mathematics. it will be definitely better. I would think, because here you would need to implement some rotations.
Oh, I see. But yeah, I mean, would the number of Pauli strings even be, because you said that the long norm had that reduction by a factor of D, but the actual number of Pauli strings
still will be D
to the 4, but with an additional 1 squared.
Yeah, so you need to think how can you efficiently compile this problem, but you have a lot of structure. This is what I can tell you. For example, you look at these coefficients, they're the same for all electrons. What you do, you just move your matrix into different tensor product. So the question is, can you make use of this in order to compile it more efficiently? Yeah, this is an open question.
Okay.
Can you tell us about
Yeah. So basically, we didn't consider it on this work. Haven't done work on this myself, but what I know is that so if you there are some asymptotic costs, and basically asymptotically this cost will be lower than the full QPU circuit. This is why in many works on the resource estimation, at least for fault tolerance, we don't consider this. But if you would like to use it for near term, of course, you need to take it into account. This is not a very simple, operation. Partially because it's if I give you some function, you want to unsymmetrize it. This is not reversible operation, right? So you will need some ancilla qubits and do some people apply some sorting algorithms to do unsymmetrization. So yeah, it's a good question. We need to cause this and see how it performs.
And do you think that there could be a sort of more complicated that includes that, or it's not really?
What do you say?
Because for instance, in second compilation there is this nice thing that would just the Jordan ignore takes care of this all the sets. Do you think in that setting there could be a mapping that kind of has the same effect, or it's just?
Yeah. So if you prepare your state, which is symmetric, and then you apply time evolution operator, then the state will be still antisymmetric. But then the question is, what is the what do you do? Yeah, it's an open question, I think, with the initial state preparation. And I haven't seen. There are works on how to do it in fault tolerance. I don't know many. I don't know. Okay, maybe there are works, but I haven't seen people analyzing the details. Yeah, maybe for some small systems like 2 electron, people did this work, of course, and wrote down the circuit and do it on a simulator. I don't know how generic it is, and definitely not in an arbitrary basis. People did in a real space.
Questions? Okay, let's thank Aleksei. While we're here, and we've got a very full room, this term's program is basically packed and full, but things for next term we're still looking at. If people would like to make suggestions, please send them, probably not to Jara, actually, probably more to Lilo, actually, yes, in there, including things like, would people like tutorials on how to do these things?